So here's my next Scamp project. So I want to get into astronomy, so my thought is I take the Scamp camper out camping. Usually there's a picnic table nearby. And there's the sky overhead. And up in the sky there's stars and planets, constellations. And maybe even the International Space Station's going overhead. So what I'd like to be able to do is have some sort of device I can put on the picnic table, tell it I want to look at one of the things in the sky. Maybe I'm looking at Mars. And have a laser on some sort of gimbal that points at whatever I'm interested in looking at. Or I could even be looking at for the IIS if it happens to be going over at that time. What made me think of this was one of my trips down to New Zealand. I went to Lake Tekapo, and Canterbury University runs an observatory on one of the big hills up there, and it's very black nights up there. So this sort of gives you an idea of kind of what it looks like when you go up there. Really neat trip if you're ever down South Island of New Zealand. Try and go on that trip. It's a great way to see stars. But that made me think of using laser to point at things in the sky to make it easier to see where they are, because that's basically what the people from the university do when you go on one of these trips, is they're pointing out interesting things to look at from Lake Tekapo. So I started collecting things that initially I thought I'd need. So I found a laser on Amazon, this gimbal that I could control. This software seemed to be good software to use. It's in Python, and then a couple of YouTube videos helped me with understanding how to do the coding. And I'll put the links for all these things down in the description below. So I decided it's time to write some requirements. So basically thought first I'll be out at a park or something, so not necessarily have internet, so this thing's got to be able to run without a connection to the internet, be self-contained, so I can take it out and not have to worry about whether I've got a Wi-Fi or cellular connection available. It needs to be simple. By the time I get to use this, I'll probably forget the details of how it was all put together. So basically all I want to be able to do is select some sort of astronomical object like a planet or a star, and have it point the laser at it. And it's got to be fairly rugged. So again, I'm going to take this camping, so it's probably going to be bumped around inside the car in a trailer. So maybe it needs to go in some sort of box that I can lift the top off when I take it out. Also, it's got to live in the elements, so can't blow up if a little bit of rain gets on it, so it needs to be fairly strong. It can't be too expensive. I don't really want to spend more than maximum of $200. Maybe like to be able to keep it under about $100 for all the parts for this. Because I'll be out camping, the best I can hope for is have a 5-volt or a 12-volt battery available to run it on. Both those should be available. And then I want to use what I know. So basically I want to be coding in Python, I think, for this application. Use VS Code as my IDE. Use Git to store all the source code. Probably use I2C to connect the bits together. Then looking at the pieces I need after getting an idea of what I'd be using and how it's probably going to work, is I'll probably use a Pi Zero. I'm used to using those. They're pretty low cost, and basically gives me a little Linux computer to run things on. So these bits here, I probably need to know, or I will need to know where I am and what direction I'm pointing at for it to be able to point the laser at the correct part of the sky. So I'm thinking I need some sort of magnetic compass that connects through I2C, and also probably need GPS. and GPS I can get my exact location as well as get the exact time, so both those are needed when calculating where things are in the sky. Okay, we'll use a 2-axis gimbal, and initially I'm going to use that one I got off Amazon. I think that should work, but I haven't got it in yet, so I've got to test that out, and we'll attach one of those laser pointers to it somehow to have it point to all the positions in the sky. And then the other things I think I'll need is an OLED. I'm thinking I'm going to set up the OLED to work a bit like my 3D printer, where it just has some basic menus and has a rotary encoder with a button on it where I can select something from a menu, press the button, and have it do that thing. Again, the interface is going to be simple, so it's probably going to be a menu where I can select stars and constellations and things, select the specific one that I want, and then press the button, and the gimbal and the laser will go off and point at what I want to have a look at. So based on this requirements and all the pieces I think I needed, I put together a test setup to make sure I could talk to all the things like OLEDs and servo motors and things. So that's what I'm going to have a look at right now. Okay, there's my little test bench for testing out all the components I'm going to use for my sky pointer laser thing. So some of the things on this is got a Raspberry Pi Zero here. I've pulled off the I2C connection onto this breadboard, and that's driving this OLED. And this board here is I2C to servo driver. You can use I2C to program pulse widths for driving a servo. And the other I2C board is this magnetic compass device here to find directions. I'm receiving serial information from this GPS device here. This is a Rotary Encoder. It's got a switch on it as well. So I use that for menu selection in combination with the OLED. And also got the actual servo. So coming off the servo controller board, I'm pulling off a couple of signals. One goes to the servo, so we'll see that move. But also, while I'm watching that, I've got a connection out to a oscilloscope, so we can see the oscilloscope trace and the pulse width changing, hopefully. The final thing I've got on here is this little laser component. See, I've turned it on here. You probably can't see it very well, but it's a green laser. You can see the dot there. And that seems to be bright enough to make a line when I use it at night. So they'll be used on the pointing device to actually point at the planets and stars and things that I'm interested in. So let's have a look at the servo tester. So it's using a PCA 9585 device, which converts I2C commands into pulse widths for driving a servo unit. And I've got a bit of code here where it just moves the servo between 0 and 180 degrees. And I was also playing with this set the pulse width range between 650 and 2600. The normal range is 1000 to 2000 by default. I just wanted to see if I could extend the range by doing that. So let's try running it. So it's running, it's moving the servo 5 degrees at a time, and then it'll go back to 0. The other thing I'll show in here is my oscilloscope that's connected up to the servo as well. So we can see the pulse width here, so you can see the duty cycle going between, I think, about 5% and 13%, and I see the pulse width, and that varies based on what I set here as the pulse width range. It goes up to 2600 and then starts at 650 again. That all seems to be working. Next thing I tested out was using a OLED. I actually wanted to use a larger one, but at the moment I'm just using the 0.93 inch OLED. So it goes through, does a scan as well, shows some text. So this is, I'm going to use it for a menu system in combination with my rotary encoder and the switch on that. So it shows it for 5 seconds and then hides it. So let's run that. looks good. So next one I'm testing out is the encoder tester. You can see it here. I'm using a library to get the encoding values. Let's run it and it should show me the values when I turn the knob. The next test is just connecting to the GPS device. It does that through serial, again using some libraries, and it keeps reading the data coming in from the GPS and pulls out where it's available, date and time, and the location and the altitude. And once it's got all those values, it prints out the final value. So let's try it out. There we go. It's got my latitude, longitude, and current date and time, and the altitude in meters. And the final device I'm using here is a magnetic compass. It's really to get the bearing for when it's calculating where to point the laser. Again, I'm using libraries for that, so let's run that. And there it's showing some positions. Let me just move it a little bit. And you see the bearing change when I just move the device a bit. I think this is going to need some calibration as well, but seems to work. I seem to be able to talk to it. Next thing to build was the 2-axis platform that the laser is going to sit on. So I really just followed the instructions from Yahboom, and they've got some good instruction videos as well. So I just wanted to show you the stages, but it ended up taking me about 45 minutes to put it together. They give you lots of extra parts, so you don't really have to worry about missing parts. And you can just see the instructions are available as a PDF online as well. So go to the Yahboom site and you can download those. So once I'd put all that together, I wanted to test it out. So I had a couple of servo test drivers here, so I've just got those in auto mode running the servo. I was interested in how much power I was using, so using about half an amp at 5 volts to drive the two axis on the platform. So just checking on those driver circuits, we see the pulse width and the pulse duty cycle here. So we see the width is basically going between a minimum of about 1,000 microseconds to 2,000 microseconds, kind of what you'd expect for a servo. And the duty cycle's going between 5% and 10%. So we'll probably have to adjust the mins and maximums to get the full range of movement out of the platform servos. So I got some plywood just to try mounting things on and see how it's going to lay out. So this is the 2-axis gimbal. Probably GPS will go up here somewhere. Raspberry Pi over here. I'll have this board in the middle. It'll just be a bus for things like I2C and maybe the serial connection up to the GPS. This is the servo motor controller, I2C there. OLED, I2C. And then the Rotary Encoder with the switch on it. I'm going to add this in here. This is just will be a 5-volt power supply. There's plenty of current generated by this, and it's plenty to drive the servos here. They seem to need about half an amp at peak. And then some of the other things I'll throw on here is just a little leveler, because we'll need to make sure the whole thing's level when it's pointing at different places in the sky. I'll throw a compass on. I've got these little compasses, so I'll throw that on just to help me with direction. But we've also got this electronic compass here, so between the two of them I should be able to work out that it's pointing north. That's going to be about it. I probably won't use this board in the end. I'll get a better looking one. I'm also going to put some screws in the side, or thumb screw type things, where I can adjust the level to get the whole thing level, because this is probably going to be set up on a picnic bench out in the park somewhere. Next thing I needed to do was make a laser mount onto that 2-axis gimbal. So I 3D printed it again using Fusion 360 to design it. So this is what the design looks like. So basically 2 pieces. So this top piece here, that actually holds the laser in there and mounts to the top of the gimbal, and then there's a space for a 18350 battery here, rechargeable battery, which is enough to drive the laser. And then there's a piece that goes on top of that, sort of flips over this one, and this holds a button to turn the laser on and off, and the top of the contacts for the batteries. So I printed that up, and let's have a look at it. This shows how the laser holder fits onto the gimbal, and here's where I'm gluing the contacts for the battery and the switch into the various pieces. This shows the laser holder mounted on the gimbal. It's all working. I can turn it on and off with a switch. So I think this is a keeper. We'll use this. So I used Fusion 360 to design some holders for the various components that go on that board, just so I could screw them down. So here you see them for things like the GPS and the UPS and the Raspberry Pi module, all sorts of things. So made these, printed them out in 3D, and used that to make sure I could screw the components down to the board. So this is it mounted on the board. I added these holders so I could screw them into the board so things don't move around. This is probably more the layout I'm going to have: GPS, Raspberry Pi board, the bus board where I have all the connectors going, the servo control board, and this is a UPS power supply. Can provide up to 3 amps at 5 volts, so will be plenty to drive the servos, which are the main power consumers. One interesting thing, so I tried using these magnetometers to find the direction of magnetic north. I wasn't having much luck with it. I actually tried 2 different devices and 3 lots of different pieces of Python libraries. I did some calibration. I still couldn't get it pointing reliably to north, so I think I'm going to change the course on that, just take those out, and I'm going to put something like a little magnetic compass on there, and just have the whole board point north, which should be easy enough to do on a picnic table. I'll just line up those, point it north, and then I'll probably do have a calibration option to point at Polarus, just to make sure I'm actually have this servo pointing dead north when I'm calculating where star positions are. So I'm going to cut to the chase a little bit here. So set up a little prototyping environment. So I've put the SSD 1306, it's the 0.93 inch display, which uses I2C, and I also put the larger display I was trying out on there. That's a TTL based display using SPI to interface to it. So this is the little display. You see it's working here, kind of what I want it to do, but it's really tiny, so I don't know whether I really want to use this. It's a bit small to see, especially without my glasses on. So this shows the larger display basically doing the same thing, but easier to read. But I'm not sure whether I like this 100% just because it has 7 wires to connect up that I haven't used anywhere else. So there's a lot more wires running around the project, which I don't really like and may not help with the reliability. So I'll show you what I went with in the end. So this ends up being a SSD 1309. So it's a little larger. It's like 2 inches. So it gives me the advantage of the bigger display, but it's a lot easier to interface. I can still use the I2C interface to it. So I think this is how I'm gonna go. So I'll show you the code I used to get these demos working. So for the code, I knew I needed to make within the code a menu class where I could show menus, and this basically shows the layout of the menu class. So on init, it loads up a list of menu objects. So there's going to be a menu item defined as well, which has things like the name of the item, a description, bearing information like altitude and direction to the object. And then I'll also load in any information about the actual display I'm using, things like height and width and things like that. And then I'll be calling a routine inside the class called show menu. So basically it's going to show that menu, so the list of menu items on whatever display I've got there. It'll show whatever number of menu items fits in the window. So sometimes it's going to be more menu items than can fit in the window. So it's going to use some sort of windowing to show part of the list of menu items and then allow you to scroll up and down. And basically it's going to go into a loop where it's going to keep looking at the three buttons. So I've got an up button, down button, and a select button. If it's up, then it's going to move the little pointer to show that the next item's selected. If it's down, it's going to move the pointer the other direction, so the item's selected. If we're selecting an item that's not visible inside the display window at the moment, then it just moves the window down a little bit so it can see the next set of items. That's what it's doing down here. And then if we press select, then it just sets the selected item and drops out of the menu display or the show menu, and it returns the selected item to be processed. Okay, let's have a look at the code. It really just follows that design. So run through, set up the GPIO pins that are going to be used to read those three buttons. One big change I made from the earlier code was I swapped over to using Luma libraries rather than the Adafruit libraries. I just found it gave me more flexibility for the devices I want to use. So in this case I'm using SSD 1309 rather than a 1306, and this seemed to handle it pretty well. Running through, I set up some constants. Like I said before, there's a menu item class that just defines what an individual menu item contains, so I can add to this if I want. And then inside the actual menu class, so like I showed before in the init, I'm setting up the defaults for the display type I'm using. And then I go into the show menu routine, so initialize the selected item in the window start position to 0, set the selected item to none, and then it just stays in that loop like we saw in the design until an item is selected. And then we just do two things. We process the button presses, so see if one of the buttons was pressed and do any processing that we need to do, like changing what the selected item index is or the window start index is. If one of those up or down buttons are selected and we still haven't selected an item, then it'll display the menu. Otherwise, it'll just return the selected item like we saw and drop out of the show menu routine. Here's the process button code. Nothing too exciting there other than following my design again. Jump down here, display menu on I2C. So this is how it goes through the list of menu items, starting from wherever the window start position is at the moment. So again, if we've got more items than fit in a window, then that start index may be something greater than 1 or 0. So it goes through, shows all the items. If the current selected item is the item that we're showing at the moment, it puts a little greater than sign next to it to indicate it's shown, otherwise it's just got a space before it. Draws the text and displays the menu. So finally I was just checking on the layout of items I'm going to put on the board. I'm going to actually have a better board in the end. But I'm going to put most of the components in the center so I can cover them with a box so you don't have wires everywhere. You can see the things connected up all seem to work now, so the menu and the buttons work. I also checked out the servo works, so I did check the GPS still works, so got all the bits working. So for the next video I'll concentrate on the code to get all the bits working together and actually point to some stars. One thing you notice is I also removed the batteries that I had on the board. I think I'll just have a USB connection to get the power rather than always having batteries sitting on the board. It gave me a bit more room as well. Here's a better view where I 3D printed a case to go over the centre part, so I've got most of the components covered now. Still got the ugly board underneath, so I need to clean that up with a nicer piece of wood, but otherwise this is most of the pieces. So this is what I think I'll be doing in the next videos. So in the next video I'll review the overall program design, and you can kind of see the template for that in the background. Then I'll code this up, and I'll be using Python astronomy libraries. That's probably going to be the most interesting part, so I'll see what fun I have with that and highlight any interesting bits in the code. Once that's all working, then I'm going to need to calibrate the servos to make sure they're pointing at, you know, whatever degrees elevation I have and whatever bearing I set, make sure it actually points to those places, and then test it out, make sure I can point to some of the stars I think I want to be able to point at. And that's about it for most of the testing. Still a bit cold now, so I'm not going camping yet, but in a month or so I'll probably go camping, and that's going to be part 3. I'll show it working, make sure it works, make sure it, when I take it out in the wild and sitting on a picnic table, that everything's still calibrated, will still point in the right direction, and I can actually find out where the stars are in the sky.